This is this is the second part of the video. Before I start, I want to go back to policy iteration and value iteration because I think I didn't explain very clearly in my last videos. So policy iteration, there are two parts in policy iteration. First is you evaluate the value functions. You iteratively evaluate the value functions, and then you generate a better policy, pi prime, which is give you using the value function. So imagine you're in a maze. A policy so a policy iteration would be updating the either the state value function or value action value functions in the matrix together with a policy. The policy defines, at each position in the maze whether you're gonna go left or go right, go the steps that you're going to take. So basically, a policy iterations not only update the value functions but also update the policies. Here in a generalized policy iteration, you can use any methods to evaluate the value functions, either Monte Carlo or TD. In control problems, you can also use a action value functions Q, and the policy would be just derived by comparing the Q values. If you're just using a state value function V, then a policy would be derived from comparing the state value functions. Moving on to the next state, which action moves to a better state. So the actions will be derived from state value functions. But here in evaluating the policies can use either Monte Carlo or TD learning, and you can use either the value function or the state value function or the action value functions. Comparing value iteration to policy iteration, value iteration does not have an explicit policy. So going back to the previous example of, in a maze, a policy iteration would have two matrices. One is the matrices of the value functions. The other matrix would be the policies. All the directions that you're going to take at each state or positions. But value iterations, you're just going to use Bellman optimality equations to constantly update the value functions without mentioning an explicit policy. So I want to make that clear before I continue the videos. So hopefully that makes things clear. So last video I talked about function approximation using differential functions such as neural networks to replace the state value functions V or action value functions Q. So the idea is basically just to parameterize the value functions with an additional weight factor called W, and use you calculate we can calculate the gradient of the W respect to the loss functions, which is right here, and then we can update W in the directions of the gradient times the learning rate or step factor. So we can represent the state by a feature factor, and then we can represent value function by a linear combination of the features. The feature factor, the value function would be the matrix multiplication. That would be the multiplications of the feature factors times a vector of the weight. And then if we want to update the weight, we would calculate the gradient of the weight, which would equal to the learning rate times the difference between the value functions and the current approximated neural networks value functions times the feature factor. This is also called the prediction errors. So the weight would be updated in the directions of this update. Again, this is reinforcement learning. There's no supervisor given, so we do not have a labeled training or validation data. So we don't really know what we're going to use what we're going to use for the target. So in reinforcement learning for MC, TD0, TD lambda, we replace the corresponding evaluations. We substitute the target with the corresponding evaluations using these learning methods. So for Monte Carlo, we're going to replace V pi s with GT with the goal. And for TD0, we're going to replace with the with the TD target, and then for TD lambda, we're going to replace the TD target at we're going to replace the TD target lambda. Here in this slide, it's saying Monte Carlo with value function approximation return is unbiased. So basically, we can apply supervised learning to all these training data, and we can learn the weight per W. And similarly, we can also apply TD learning, although it's by samples, which is taking one steps or a few steps, but we can still apply this supervised learning method to quote unquote training data to update the weight. Similarly, this is TD0. Similarly, we can update the weight with TD lambda learning method. So these three slides just gives the exact equations to update the gradient of the weight. So using these methods, you can just substitute V pi s with these learning methods. Instead of updating the so here we are parameterize. So we define a feature factor x, and we times a vector of weight, which is the approximated value function for v. We can also parameterize q. So this is what the rest of the lectures is trying to explain. We can also parameterize q with an additional weight called w. Similarly, you can use chain rule to find the gradient. So this is how you're gonna this is the gradient of the weight, and this is how you're gonna update the weight. Here we're again representing the state action value using a feature vector. Here, since we're updating q, we have both s and a. We're timing a vector of weight, and we're just gonna update the gradient of w using the gradient of the w. So similarly, you can use all these methods, MC, TD0, TD lambda, forward view, backward view of TD lambda to update the target functions. The same concept as before, but here we're updating the q we're updating q instead of v. This is a slide showing if we should bootstrap. It turned out that it worth the efforts to find out the lambda values, so that it gives you a better idea. It helps you to find the sweet spot. So you can use stochastic gradient descent, incremental methods to update w. You can also use a batch methods to fit the value functions, giving the agent experience, or we can also call it quote unquote training data. The idea is you're given an experience with a set of state value pairs. We're just gonna use least squares algorithm to fit a function that can minimize the sum squared error between all these pairs. So we're given an experience D, consisting several state value pairs, and we'll be just calculating, we're just fitting a function that minimizing the sum squared error between the target values and our approximated parameterized value functions. So a stochastic gradient descent with experience replay would be, given a set of experience, we will randomly sample these. We'll select the mini batches from this experience, and then we'll update the weight using SGD. One of the examples, one of the algorithms he explained in the lectures is called deep Q networks, which is also used to train the famous Atari games. I think I have a slide here showing that using this method to train Atari games is quite successful, and majority of the games trained using DQN surpassed human levels capabilities. But the basic idea of DQN is to select mini batches, is to sample from the experience replay and use that to update the target, the fixed Q targets. So since we're sampling from another set of experiences, we're not learning on the go. This is the off-policy learning method. I guess I'll quickly go through the algorithms so you know what I'm talking about. DQN use experience replay and a fixed Q targets. This is the targets that we want to update. A will first take actions AT at time step t according to the epsilon greedy policy. So it will be randomly taking actions according to the epsilon greedy policies, and then it will store the transitions in this replay memory called D. The transition would be I'm at time step t, I take an action AT from the epsilon greedy policy. I will receive a reward on the next time step, and I will reach to the next state, and then I'll reach to the next state. I'm gonna store this in the replay memory, and then I will randomly I'll randomly select mini batches of such transitions from D. Okay, and then I'm gonna use Q-learning targets. I'm gonna compute the Q-learning targets, which is this part here, with respect to old fixed parameters W minus. And then I will optimize the mean squared error between this Q network and the Q learning targets. Okay, it's probably daunting to look at this equation here, but if you look at this equation, if you look at the slides on the right, this is I copy pasted from lecture 5, SASA Max, which is an off learning method. You will notice that equations on the left is pretty much the same as the equation on the right. You're updating the Q functions using the max action value functions in future states. And here we're also using the action value functions from a future state and the future actions parameterized to fit this loss functions. So there are actually two kinds of policy there are actually two kinds of neural networks, which is explained here. Because this is off-policy learning, there are two neural networks. One is called a policy net. The other is target net. Target net is what we're going to update, but we're first taking actions from the policy net using epsilon greedy policies. Once we have this replay memory, we will randomly select the made batches from D, and first we'll optimize this policy net. And the next actions will be also selected from this policy net. The target net will be periodically updated either through hard update or soft update using the policy net. A hard update would be just directly copy paste from the policy net. A soft update would be just taking a weighted sum of the policy and the target net. So this is how DQN works. We're not directly updating the target net, but we are actually updating a different neural network called policy net, and then periodically copy paste the policy net to the target net. So this is the Q-learning algorithm for off-policy control from lecture 5. If you compare DQN with Q-learning, in Q-learning, he's also taking an action from S. Remember, Q is a function of mapping state to actions. So he is choosing actions from state using the policy derived from Q, using epsilon greedy. So here, he's also taking actions according to the epsilon greedy policy from the policy net. So there's several advantages of using two set of neural networks, which is explained here. If the policy network rapidly changes, its Q-values predictions for future states would fluctuate, making convergence difficult. So he's only updating the target functions periodically from the policy network. Without a target network, the same network would generate both current Q and future Q, creating a moving target non-stable learning. So, okay, the loss function compares the policy network Q-value prediction, again, target estimate. Only the policy network weights are updated during backpropagation. The target network remains frozen. So in this slide, we're actually the loss function is actually calculated from the policy network, policy net. Yeah, I think this is what's missing here. This is only updating the policy net. The target net is separated. It is only updated after policy net. It is only updated after policy net is updated, and it only updated periodically using either hard update or soft update, so that we can separate these two different neural networks to stabilize the learning. So this is DQN, a model-free off-learning methods to evaluate the action value functions in order to update the policy network, in order to eventually update the target policies. And you can also use a batch method, which is just do a least squares, fit a function using least squares method. Instead of gradient descent, but this would involve finding out the inverse of matrices and stuff like that. It's probably compute extensive, but it's another option if the dimensions is not that big. So lecture 6 is about using neural network to is about approximating the value functions, either state value function or action value functions, to in this policy iteration in this policy iteration models to constantly learn and update the model. In the end of the lecture, it also mentions the method of DQN, which use experience replay to an off-policy learning method to update the target policy. But eventually, all the methods, I think, follows into this policy iteration idea that in order to constantly learn improves the agent model, you will have this loop, you will have this iteration of constantly evaluating, learning, and improving. So I think this is real. I think this is really important to understand policy iteration and value iterations. DQN is also a policy iteration because it does have a it does have it does update its policies explicitly, unless just updating the value functions. So that's lecture 6. Lecture 7 talks about policy gradient. So previous lecture we were only approximating the value functions v or q. What if we can directly parameterize the policy pi? So this is what this lecture is focusing on. Also, this again, this is model free learning. We do not have a world model. So this slide is just explaining the differences of value-based and policy-based. Previously, we have policy-based. We learned a value function with implicit policy, such as epsilon greedy. A policy-based will have no value functions, and we will directly learn a policy. Actor critic would be learning both functions, or would be learning both value functions and policies, and then use that to update the model. This slide is explaining that a policy-based RL can learn the optimal stochastic policy. I remember in the lecture David talked about, if you're using value-based, and use the value-based to implicit select the actions, you'll probably never be able to reach the goal. You're just wandering left and right. Where comparing to a policy-based RL, it added more stochastic randomness into the policy. So sometimes it will go down in order to reach the goal here. So I think this slide is trying to say that we should have a policy-based method would be able to learn such stochastic policy, because sometimes that would help us reach to the goal. But how would you define a policy objective functions? Here it lists three methods. Given a policy with parameters theta, find the best theta. you can either define you can define the policy with just the start value, using the start value, or you can, in a continuing environment, you can use the average value. D is a distribution. Okay, so it's just a probability. You're just yeah, depending on which state you're at, you're just times the v with its corresponding probabilities, or you can take the average reward per time step. So instead of instead of using the value functions, you can directly use the reward times the probabilities of taking the actions and the probabilities of each of the states. Several methods to optimize the policy, but I think he's gonna again use the policy gradient methods. But since we're finding the we're search for a local maximum, because we're trying to calculate the reward here. He is doing a gradient he's not doing gradient descent, but gradient ascent. So he's going to calculate the gradient of theta. If if it is not differentiable, you can use a finite difference to find out the gradient. In order to calculate the gradient of the policy, he used a trick. So the gradient of the policy would be the policy itself times the gradients of the log of the policy. So it's basically just is using a trick here. He to calculate the gradient of the policy, he times and divides the policy itself. This term here would be the gradient of the log of the policy. So the score function is so this is the score function. Depending on the types of policy you use, softmax or Gaussian, this is the score functions. If you calculate it using chain rule, you'll be able to get to these equations. A one-step, consider a simple class of one-step MDP terminating after one time step. The gradient of the policy would be as follows. So the gradient of the policy would be the gradient of the log of the policy itself times the reward times the corresponding probabilities. So the policy gradient, so here he defines the policy gradient theorem. In order for any differentiable policy pi, for any of the policy objective functions, which I explained earlier, the policy gradient would be the expectancy of the gradient of the log of the policy times the q functions. So if you compare this equation with this equation, he's just replacing the instantaneous reward r with the long-term value q here. So replacing this r with this q. That's the policy gradient theorem. If we use Monte Carlo in the policy gradient theorem, we would be just replacing this q with Monte Carlo learning. So So using return VT as a non-biased sample of Q pi. So he's just replacing this VT. He's just replacing Q with this VT because we're doing sampling and then constantly learning and updating the theta. So that's policy gradient. Instead of learning fitting a value function to implicit find out the policy, we can directly parameterize the policy and update theta. That would directly tell us what is the policy. But it has such method has high variance. Monte Carlo inherently has a lot of high variance. So here it talks about a actor-critic policy gradient method. He's using another critic, like a judge, to help him update theta. A critic updates the action value function with parameters w, and then the actor or the agent itself will update theta in the direction suggested by the critic. So this method will be simultaneously updating two neural networks. One is updating two functions. One is the loss functions for the critic, and the other would be the policy. The other will be to update the policy, which is the model of the actor, the policy of the actor. Because theta is updated in the direction suggested by critic, so it is following a proximate policy gradient. So this method, he explained, it will reduce the variance introduced by Monte Carlo policy gradient, using with just actor without a critic. How do we estimate Q? So there's several methods you can use: MC, TD, or TD lambda. This slide explains the algorithm for action value actor critic. I think this is like a vanilla version of actor critic policy gradient method. There are many other derivatives of this vanilla version, like PPO, which is used in robotics training and other methods. But basically, this vanilla version used two linear value function approximators. One is for Q, one is for policy pi. He's gonna initialize as theta. He will randomly sample an action from the policy. For each step, he will sample the reward, sample the transitions, sample the actions from the policy, and then he will update TD error. He will adjust the actor using the Q functions from the actor, from the critic. And then he's gonna adjust the critic by updating the weight. Here he's using another learning rate beta times TD error times the feature vector. And then he's going to continuously running this loop in order to update theta using the action value functions from the critic. So that's the action value based, actor critic, policy gradient, learning method. You can replace Q with other forms. So in this example, we use Q. You can also use a so-called advantage A function that would help eliminate some of the bias and variance problems. The lectures from David explained in details how the A function is defined, but I'm not gonna explain here. But I think I've explained the ideas behind actor critic, why we need an additional critic, and how we're using a policy neural network to directly update the policy. So that's lecture 7. Lecture 8 introduced the model-based reinforcement learning method. So all previous lectures, we focus on model-free learning. With no model itself, we're learning the value with no world model. We're learning the value functions or policy from the experience. Here, instead of learning from experience, we will directly build. This method directly builds a model, and use this model to predict the value and policies. There are several advantages because, we can learn such model by supervised learning. We can reason about the model uncertainty, but in order to learn such model, we need to construct the value function. There are going to be two sources of approximation error. First is, whether this model is accurate, and then using this inaccurate model to predict possibly an inaccurate value or policies. There are two sources of errors. Here he defines the model M, which is the probability eta and a reward function eta that would help predict the next actions and the next reward given the current state and current actions. If we have a list of experiences, we can use supervised learning method to build a model that can find out these probabilities. One of the methods he mentioned is called a table lookup model. I guess I will not go through the rest of the slides. Moving on, he talks about various iterations of architectures, including a simulation-based search, I think, which is the method that he used to train AlphaGo. Lecture 9 talks about exploration and exploitation. So far, he covered greedy, epsilon greedy, but in this lecture, he talked about other methods like delaying, epsilon greedy, and a few other slides that I did not copy paste here. But I think you get the idea so far that an agent, in order to learn, we need to give the model the ability to randomly explore in order to find maybe a better path to reach the goal. But at the same time, it also needs to exploit in order to maximize its current reward to update the value functions, updating the policies. the last lectures he talked about how reinforcement learning is used to train agent to solve some of the classic games like Go, chess, how it reached superhuman grandmaster level, beating the world champions. He talked about Nash equilibrium, which is, in order for each players to win, the ultimate state would be that each player has the best policies of its own. This is the ultimate state that each of the agent would reach. He talked about zero sums, minimax, which is in order for, so he's basically just going to build a tree where two players playing against each other. One player would be trying to maximize the value function, the other would be to minimize the value function, and one is maximizing, the other is minimizing. Eventually, they will reach Nash equilibrium. So he's going to constantly. So here he explained how he used minimat search to solve the chess problem. Yeah, I don't have the rest of the slides here. But if you look at David Silver's lectures on YouTube, if you're more interested, you can go through them, which explains in details how he used Minimax to solve the chess problem and the Go problem. But I think so far I've explained some of the basic ideas and concepts used in reinforcement learning, the structures of MDP, some sampling-based learning method called Monte Carlo MC or temporal difference TD, the forward view, backward view version of TD, on policy and off policy control, how using networks to approximate the value functions, and how parameterize the policy itself can and use that to directly learn a policy. With that, I guess I'll close the video. Hopefully you learned something today.